Hi girls, so I'm going to go through the answer to the example of Taylor going down the slide, and again I'll use my trusty notebook here. So part A says state the size of the net force on Taylor. When you read the question, it does say she has a go on the slide, and as she is sliding down her velocity is constant, and there is your clue. If there's constant velocity, then that means the net force must be 0. So constant velocity equals a net force of 0. So that's your answer to A. Okay, Taylor's mass is 65 kilograms. What is her weight? That's revision of year 11 work, F equals mg. So therefore her weight force is 65 times 9.8, which gives you 637 newtons. Okay, now the next one asks us to, on a diagram, draw the forces as labelled vectors acting on Taylor. So I've drawn a very simplified Taylor here on her very simplified slide, and we're going to, sorry about the noise, I'm just looking for a different colour pen and dropping a whole lot of things in the meantime. Must be a bit weird you listening to this at home. I'm on my dining room table. Okay, so from the centre of Taylor, we've got a weight force acting directly down, and then we've got a support force which is holding her up on the slide, and that always acts at 90 degrees to the surface. So we'll put a little note there. Support force, which is Fs, always acts at 90 degrees to a surface. Okay, and then as she's sliding down, there is also some friction. Okay, so and that frictional forces always act along a surface. Frictional forces, which is Ff, always act along the surface. So there is your answer. They're all of the forces acting on Taylor. It's actually her weight force. If you're asking where the thrust force is, it's her weight that is causing her to go down the slide. So there's not a thrust force on top of that. Okay. Section D, complete and label a vector addition diagram of the forces acting on Taylor. Now her velocity is constant, so these three forces need to add to a net force of 0. Now when we've got 3 arrows, the way we do that is to form a right angled triangle. And the easiest place to start is with the weight force, because you know the weight force always goes down. So let's draw that in first. That's the weight force, and we know that that's 637 newtons. And then what we're going to do is put these, oh, you can't see, hang on just one moment. There we go, that's better. Then we're going to put these two forces on the diagram, and we're going to add them nose to tail. So I'm going to take this force, and it's like picking it up and putting it on the end here. And when I do that, and notice that they are at 90 degrees to each other, so that's where your right angled triangle comes in. So here, oh, sorry, here's my right angled triangle. We've got F, F there, and F, S there. Sorry, it's a bit messy. Okay, and that's your right angled triangle. So when we add those three forces together, or we add the square of this and the square of this, it equals the square of this one, and that's how we get a net force of 0. So that's complete and label a vector diagram. That is part D. And then part E says to us, the top of the slide is at an angle of 40 degrees to the vertical, calculate the value of each force acting on Taylor. So here is your 40-degree angle there. And so we can just use Pythagoras to calculate F support. And to get that, it would be opposite over hypotenuse, so sine 40. So F support is 637 sine 40, which is 409 newtons, and the frictional force is 637 cos 40, which gives us 488 newtons. And that is the answer to there. Okay, so if you like, here on the slide, that's your 40-degree angle there. So we've just, yeah, that's how it gets to be here on the diagram. So I hope that's helpful. What I suggest you do now is go away and write that up in your notes, and hopefully you can see all of this. Okay, well done.